Well, good morning. This is Chapter 7 on inductance and capacitance and the DC response to capacitors and inductors. So this is kind of a two-part chapter. We look at some equations for capacitance and inductance, and then we talk about transformers having to do with inductance. And then we go into another area where we call up DC response to capacitors and inductors. So this is a chapter that has a lot of different parts to it, but basically it's an introduction to the idea of what is an inductor and what is a capacitor. And we treat it from a mathematical point of view, and we also treat it from a practical point of view. What are these devices, and how do we implement them in a circuit? And then also we have not yet talked about, but coming up will be how we implement these in AC circuits. But right now we're just talking about them in general. So the first one is we talk about is an inductor, and we can look at the equation for an inductor. It's voltage equals inductance, or L, times the derivative of current with respect to time. So that's a fundamental equation that you can carry around with you, kind of tuck it in your pocket and say, okay, that's an equation that, while I may not remember it exactly, if I remember the guy Eli, and I don't know who Eli is in this case, but ELI, voltage leads current in an inductive circuit, or ELI, E equals L di over dt. If you can kind of carry that around with you in the back pocket, it might at some point in time kind of give you a little bit of a feeling. Yeah, I can kind of understand why this is a little bit different than resistance or other devices, but this is the fundamental equation for a pure inductor. Now, most inductors are not pure inductors. They've got resistance in them, so basically there's always some R floating around there. But basically, if we did have a pure inductor, this would be the value of how to find, for if you had voltage, how to find current, or if you had current, how to find voltage. So we're getting into calculus, and I know that's something that probably some of you are not too familiar with, but just remember that it's the change of current with respect to time, or the change of voltage with respect to time. And that's all we're talking about. It's if there's a change. So E equals L di over dt. For a capacitor, it's I equals C dE over dt. So it's Eli and then ICE. And those are the two equations that you can kind of tuck away and remember, and then maybe sometime you would actually be able to use those. But for right now, we're just going to say Eli and ICE, and then we're going to go ahead. Next is the idea of a transformer. And the transformer is an inductive device that allows for voltage to go through and then come out the other side at a different values. So it's based on the turns ratio, the number of turns of the primary windings and the number of turns of the secondary windings. And voltage goes with the number of turns, and current goes against the number of turns. So basically, if I have a higher number of turns on the left side and a lower number of turns on the right side, it'd be like a big gear and a small gear. And this would be my voltage. This would be my voltage over here, big to little. Current would go opposite, so this would be big current and this would be little current. So voltage goes with the turns ratio. And here would be high voltage, low current. Over here would be low voltage and high current. Here would be small number of turns on the primary, high number of turns on the secondary, little to big, so little voltage to big voltage, low voltage to high voltage, high current to low current. So there's a balancing act. There's a low and a high on each side, and the voltage goes with the turns ratio, current goes against the turns ratio. Here is an example of why we would use transformers. So I have a power plant, and I start from the power plant, and I move through some transformers, and I get that voltage up to a high voltage, small current, and then I can transfer that or transmit that voltage down some transmission lines, and then at some place like your house, I can transform it back down to a lower voltage, and then we can use it at a lower voltage. But this is high voltage. You wouldn't want to touch this with a 10-foot pole. Over here you would have low voltage to high voltage and then back down. Overall, with this situation, with this arrangement, we lose a lot. We lose about 2/3 of the energy that was originally generated over here is lost. It either goes up the smokestack, it goes in losses in the transformers, or it goes in losses over the transmission lines. But someplace along the line, there's a loss, and it all adds up to about 2/3 of the total power that we started with over here gets lost in the process. So 1/3 is about all we can get, and that's one of the reasons why electric energy costs more than natural gas to heat your home. So if you talk about which is cheaper, you always say it's about a 3-to-1 ratio, and it is, because this chews up, in this process, it chews up about 2/3 of the available energy. Another thing we talk about with transformers is this thing called flux, and that's why it only works with AC or a time varying signal. If you say it's a DC signal, it will not work through a transformer because there is no change in the flux. The change in flux over time is what allows the transformer to actually work. So we go through this dphi over dt term, and we come up with this idea of the flux on the one side equal to flux on the other, so that the change in flux on the one is equal to the change in flux on the other if there's no losses, and there always are, but we pretend that there's not. So we come up with this idea of a turns ratio, and V1 over, or V2 over V1 is the turns ratio of N2 over N1. So we talk about the turns ratio, and here's an example. Here I have a turns ratio of 5:1. My voltage on the primary is 10, so what would be my voltage on the secondary? It would be 2 volts. Now we can go and find I over here. It's 2 volts over here. I would be 0.5 milliamps. And is this AC or DC? This is AC current. This is an AC current. So now I have 2 volts. I have 0.5 milliamp. Now let's go back and find out what the current would be on the primary side. Well, this is big to little. So this would be big to little. So this would be 0.5 milliamps, and we would go 1/5 of that, or 0.1 milliamp, over here on the primary side. So high voltage, low current, low voltage, high current. Balancing act, left to right, high to low, one high and one low, one high and one low. Here's another one, 10 volts, 1 to 2. So what would be this primary, or what would be the secondary voltage? The voltage over here would be 20. So 20 divided by 1K would give me 20 milliamps, right? So 20 milliamps would be the current flowing over here. So what would be the current flowing over here? Well, you would double it. It would be 40 milliamps. So do you see low to high, low to high, low current, high current over here? So you have one of each, one small and one bit large on each case. So you can do this turns ratio if you want to, but basically I just like to say low to high, high to low, and be done with it. Okay, so here's some transformers. Here's some real live transformers, and this would be what would be out in the yard someplace at a transfer station or a transformer station, and in the country someplace where you would actually see these things at. And these are the small ones. These would be the little ones that you would see in a control panel, or maybe in the back of a TV, old style TV or something like that. But these would be the transformers that you would see that would bring the voltage down to some lower voltage in some kind of a device in your home. So these would be used in a home situation. These would be what would be out to get you the power that you need in your house. Okay, so here is a picture of this primary and secondary, and this mutual flux going around. This would be a way of looking at it. It's an ideal transformer. Most are 95% efficient, so you only lose a little bit. So guess what? We got problems now. We're going to have to go through and look at some of these problems. And we're going to do that right now. I have to get reset up here, but we're going to go through it and we're going to look at some of these problems. So hang on a second, we'll get set up for that. Okay, so we've got our page up here, and we're going to be looking at some problems on page 5 of chapter 7. So problem number 1. Problem number 1, 7.1. So we have a 35 volts for V primary. We have a turns ratio of 1 to 3. So what will be our secondary voltage? Well, it's going to be 3 times 35. So we said 35 times 3 is 105. So our secondary is 105 volts. And we go through a 1K resistor. So we have voltage, or I secondary is equal to 105 milliamps. Now they want to find I primary. So if we go, okay, so over here on the primary side I have a 35, and the secondary I have a 105. Over here I've got a 105. So I want to go bigger over here than I do over here. So I'm going to go 3 times the 105. So I go times 3, or 315 milliamps. So I have a small and a big over here. I have a small and I have a big over here. Do you see the balancing act? I've got a teeter-totter, and I'm trying to figure out how to balance these two. So I got a small and a big and a small. So basically this is the right answer. So this would be my I primary is equal to 315 milliamps. That'd be problem number 1. Okay, problem number 2. So this one I have an unknown resistor. I just have a load. It just calls it a load. And I have a primary and a secondary circuit here. I have a primary, a secondary. I just call it a load. I don't know what it is, but we just say, and I have a 5 kVA. What is kVA? That's power, right? That's equal to V times I, right? And I have a ratio of 4 to 1. 4 to 1. So my primary is 480 volts. My secondary is 120 volts. So I know my voltages. And it says find the currents. So basically, if I have 120 volts over here, if my V secondary is 120 volts, what would be my current to give me 5 kVA? So V times I is equal to 5,000. V is equal to 120. What would be my current? I is equal to 41.67 amps. So, secondary, small voltage, primary, high voltage, secondary, 41.67 amps, primary, does it go bigger or little? It goes little, doesn't it? Because this is little big, big little. So I divide 41.67 divided by 4, and I get 10.41 amps. So my primary voltage, primary current, secondary voltage, secondary current, they look the same. So look, 480 primary, 10.41 current. Secondary, 120, 41.67. So primary voltage, secondary voltage, primary current, secondary current. This times this has to equal this times this. And you're in. Okay, so that's problem number 7-2. Okay. 7.3. So for this one, we use the following values. Okay, so we got a transformer. So basically, what is our bottom line on transformers? Here's my R. Transformers are pretty easy, really. Okay, so I have a turns ratio of 5 to 1. I have a primary voltage of 25 volts. So what would be the voltage over here? The secondary is equal to 5 volts. Okay. And R is 1.2K. So now I can find I secondary. It's 5 divided by 1.2, or 4.17 milliamps. So what would be my primary? High to little, big, little, big, little. So this is 4.17 divided by 5, or 0.83. So I primary is equal to 0.83 milliamps. So big, little, big. That's problem number 3. Problem number 4. We have a turns ratio of 2 to 3. So now voltage supply 2 to 3. That would be like saying it's 1 to 1.5. If you want to do it that way, you can. If you don't have to, but that way you can at least know exactly what you've got. Okay, so I have 35 over here. What do I have over here? 35 times 1.5, right? It's 52. The voltage over here is 52.5. I have a 1K resistor. So what is my current? I secondary is equal to 52.5 milliamps. So what would be my current over here? So little big, little big. So I would take 52.5 times 1.5, and I get 78.75. I primary is 78.75 milliamps. So this would be my I secondary, my I primary, my V primary, and my V secondary. V7. 57.2. So this times this equals this times this. I think I got it right. It's 52. I was right the first time. So 52.5 times 52.5 is equal to 78.75 times 35. This times this has to equals this times this. Five, we've got the same thing, and it's again, use the V1. So I've got a V1 is 45, and I've got a resistor over here of 1.2K, and I have a turns ratio of 4 to 1. So what would be my voltage across my secondary? 45 divided by 4, right? Or 11.25. The secondary is 11.25. What is the current? I secondary is equal to what? 11.25 divided by 1.2K, or 9.375 milliamps. So voltage secondary is equal to 11.25. My voltage primary is equal to 45. My I primary is equal to what? It's 9.375 divided by 4, right? Or 2.34 milliamps. So big, little, excuse me, little, big. No. Big, little, big. There we got it. And the last one. 7.6. So again, there's a lot of practice. There's a lot of practice here. But basically we can say what? Transistors or transformers for transformer problems are easy. They are. Don't forget that. So basically you have this teeter-totter approach, big, little, big, and that's all you have to remember. Okay, so V1 here is 25. I have a turns ratio of 1 to 12. I have a R of 1.5K. So what would be my V secondary? 25 times 12, right? Or 300. 300 volts divided by 1.5K. Or 200 milliamps, right? Volts divided by 1.5K is 200 milliamps. So that would be my I secondary. What would be my primary? So my V primary is 25. My I primary is equal to what? Well, it's 200 times 12, or 2.4 amps. Big, little, big. We'll pick up with in our next lecture the rest of chapter 7, which is on DC transient and for RC circuits and DC transient for RL circuits. Take care. We're going to be talking about capacitors and inductors and their use in DC circuits for a while now. And we're going to be talking about a capacitor first of all. And here's a picture of a capacitor right there, and a resistor right there, and a voltage supply right there. And we're going to close the switch. And at the instant that we close the switch, voltage doesn't immediately go into the capacitor, but it does this. It gradually goes up like this, and current goes down like this. Okay, so when we close a circuit, we can use this equation V, which is this voltage right here, times 1 minus e to the minus t over RC. So that is the equation for the charging of this capacitor. The current is this right here, which it follows that this circuit right here. So basically, if the voltage across the capacitor goes like this, the voltage across the resistor does the opposite, and the current goes like this. Okay. So in that case, what do we have? If you want to know the equation, this is the equations, and I'm not going to try to impress you with these other than the fact that the only way to satisfy this equation right here is to solve for voltage with this kind of an equation like this, or I like this. So that's why we got the voltages we got. That's a differential equation form. Now I'm going to ask you, what about this circuit right here? The different one, right? But if you Thevenize it, if you cut it here and then reattach, you've basically beaten the odds. You said, okay, I got this back to that circuit we had before, which I can use. So if you have a circuit that has something other than that, but a resistor or with a capacitor out at the right, take it out, Theveninize, put it back together, use the equations you had before. Here's a case where we have both. We have the charge and we have the discharge. Well, on the charge side, we have the equations like we had before. Right here. Right here. Excuse me. This is the charge one. This is the discharge one. So I'm going to let you have a sheet of paper for your tests when you take your next test, and I would suggest that you put these as equations on your test. So this would be the charge, and this would be the discharge. This would be the equation for the voltage across the capacitor when it's charging, and this would be the equation for when it's discharging. And you say, I've never seen anything like this before. This is new to me. Well, it isn't. Everything, not everything, but many things that we have in our that we talk about work on this principle of an exponential decay, exponential rise or exponential decay. So out in the yard in the summer when I'm watering the grass and I turn off the water, what happens to the water coming out of the hose? It does this kind of a thing, doesn't it? It doesn't immediately just stop. It kind of gets down to a point and it kind of dribbles a little bit and it finally stops dribbling. But basically, it does something like this. It doesn't just immediately stop. Turn it off at the hose, you get something like this. You turn the hose on, you get something like this. Okay? So you see this in nature, and a lot of times you see it. If you drain a tank or something like that, you get this. Like this. It slows down, but then it finally comes to a dribble, and finally and it comes to an end. Same thing with an inductor circuit. Okay, we've got an inductor here. Same thing. We've got a circuit with an inductor, and with it, we look at current instead of voltage. Current goes up with the same equation. 1 minus e to the minus t over tau, or t times r over L. With the same kind of differential equations. So, what do you do here? It's called Theveninize. You Theveninize and you get your voltage and your resistance down to a V Thevenin and R Thevenin, and then you use the equations that you had above. That's all you have to do. So here is the charging side, and here would be the discharging side of that circuit, and here would be the examples from the current for the charge and the current for the discharge. So now all we have to do is use those equations and figure out where we're going to have to use them in specific examples. Okay, so let's go back, look at the problems. And let's ask the questions, what do we need to do in order to get these to work? So again, we're starting at 7.7. And I'm going to have to take a minute here to get set back up, but I'll do that and we'll be right back with you. So we're back, and we've now got the sketch pad up, and we're going to be working on some of these problems at the end of chapter 7. So I've got a question here on 7.7. Assume the capacitor is uncharged before the switch closes. Write the equation for the voltage across the capacitor and sketch the waveform after t equals 0. So I have a 10 volt. So this is for 7-7. I have 10 volts, DC circuit. I have a resistor. I got a switch. I've got a resistor. And I've got a capacitor. So 2K and 40 microfarads. What is micro? That's 10 to the minus 6th, right? So now what it says, sketch the equation of the voltage across after this. Okay, so basically it's going to be like this. Voltage is going to go like this, isn't it? Okay, it's V equals voltage across the capacitor is going to be what? 1 minus, it's 10, excuse me, times 1 minus e to the minus t over RC, where our R is 2K and our C is 40 times 10 to the minus 6th. So what would that be? 80 times 10, that's 80, times 10 to the minus 3, or 80 milliseconds. Okay, tau is 80 milliseconds. This is equal to tau. And what would be the equation for current? Well, the current, this is the voltage. Current is equal to what? It's 10 over 2K, e to the minus t over tau, or the RC. So it's 10 divided by 2K, or 5 milliamps times e to the minus t over tau. So number 8, problem number 8. So now we're asking for a Thevenized circuit. So on for 7-8, I Thevenize and I get 10 volts and what? 2K, and then a capacitor, of 500 picofarads. Pico means what? 10 to the minus 12th. Nanos 10 to the minus 9th. Picos 10 to the minus 12th. Okay. So, again, voltage is 10. 1 minus e to the minus t over RC, where R is 2,000 or 2K, and C is 500 times 10 to the minus 12th. So write the equation for the voltage and sketch the waveform. It's the same sketch we had before. Write the current. The current is, this is voltage. Current is equal to it's 10 over 2K, or 5 milliamps, e to the minus t over RC. That's my current. Okay. Number 8. Or excuse me, number 9. Okay, so for number 9, we basically say the same thing. For 7-9, it's the R, in this case, is 20K, 30 volts, 20K, capacitance of 1 picofarad, 1 times 10 to the minus 12th, And we can look at it and say, okay, what is our okay, so what is our equation? It's 30 for voltage. Voltage is equal to 30 times 1 minus e to the minus t over tau, where tau is equal to RC. R is 20K. C is 1 times 10 to the minus 12th. Voltage is 30, or excuse me, current is equal to 30 over 20K times e to the minus t over tau. Ten So for 7-10, we have 12 volts, 2K, and 2K. And we have another 1K, and we have a 2K, and we have our capacitor. So let's 7ize this. So we've got 12, half of that be 6 volts, and 1K up here, 1K, add 1K, and we've got another 2K. So up here is 2K, down here is 2K, so our Vthevenin is going to be 3 volts, and our resistance is going to be 1K. We add our capacitor back in, and we're 0.05 microfarad, or 0.05 times 10 to the minus 6th, and you can do the rest. Okay, so 7ize. Okay, now for 7-11, okay, that's when it charges. And then for this one, we write the equation after the switch opens. So basically, it's sitting there in 10 with 3 volts on it, with 3 volts on the capacitor. So let's remember that. So in 11, we basically have another circuit. We're sitting in 7-11. We have a capacitor with a resistor across it, and that's all we have. And this is sitting here with 3 volts on it, and this is 2K. So now it's going to be discharging, so it's going to be 3 volts times e to the minus t over tau, and our tau is equal to RC, which is equal to 2K times 0.05 times 10 to the minus 6th. That's our tau, or our value of RC. That's number 11. 12, it asks you to graph, for 12, it asks you to graph current through the inductor. So for 12, we say what is the current I through the inductor, I through the L. So basically it's V over R times 1 minus e to the minus t over tau, where tau now equals L over R. So it's 8 volts divided by 3K times this equation, where our L is 100 times 10 to the minus 3, and our R is 3K. So that's going to give us our tau. Number 13. Okay, so number 13. Okay, so for 13, so 14 and 13 are really the same question, but for the first part of it, we've got so 7-13. We are looking at okay, so first of all, we Thevenize. So we've got 12 volts and 6, so we've got 8 volts. And we've got 2K up here. We've got an inductor. So when we close this circuit, this is when we close the circuit. So what would be our I? I is equal to 8 volts divided by 2K, or 4 milliamps, times 1 minus e to the minus t over tau, where tau is equal to L over R, or L is 10 times 10 to the minus 3 over R, which is 2K. So it's going to be 4 milliamps. So after a long time, it's going to be 4 milliamps. Okay. So then we open the circuit. So this is when we close the circuit. Then we open the circuit. And we have 4 milliamps, so we got 4 milliamps times e to the minus t over tau, where now our tau is what? L over R, but the R is the 6K. The L is still the 10 millihenries. Okay. All right, so that gives us our equation for when we close a circuit, 1 minus e to the minus t over tau. When we open a circuit, there it is. And again, we can skip 14 because it asks the same question. And then so again, we're going to do the same thing with the circuit of C, which is the problems in 15 and 16. So this problem is the same as the problem right before it, except for the fact that we have to Thevenize again. So 15, we start with a 16 volt and a 2K up here and a 2K down here and then a 1K over here. We're going to go right through the switch. We do the same thing we did before, this 2K over here. And then we Thevenize. So basically the first Thevenin is going to be 8 volts. And these 2K and 2K become 1K. And you add the 1K back in, which makes it a 2K. And you go with a 2K here. So now we have what? We have 4 volts. And we have a resistance of 1K up here. We add our capacitor or an inductor back in. And we solve our circuit. So the charging side of the circuit is this. It's 4 volts over 1K, 1 minus e to the minus t over tau, where tau is equal to L over R, which is 50 millihenries over 1K, or L over R, which is the 1K. So the L over R is this L and this R. Now, for the discharge side of it, you got to remember that 4 milliamps. So you got to remember the 4 milliamps. So 716, 4 milliamps is the starting point, but our 4 milliamps goes through e to the minus t over tau, where our tau now is tau equals L over R, where our L is equal to 50 millihenries, and our R is the 2K resistor. That's all that we have left. So that current now is flowing like this. It's going like this, and it's only flowing through that 1 2K resistor. So that's our R, is that 1 2K resistor. And that's all you have to do. Take care. Have a good day.